Okay, so I think now it's recorded, and then everyone online and also in person are able to see everything here. Okay, so before we start, any question or comments? Okay, if not, then I will make an announcement. Next Monday, there's a course called STATS 280. I think it's called 280D, which is a seminar. That I hold this quarter. So next Monday, I invited a guest speaker, which is a very distinguished professor, also a chair from a previous chair from UCLA. So he will be presenting on Monday. So if you're interested, he's also doing lots of graph, and then the topic that he told me that he would talk about next Monday is called ERGM, which is called exponential family random graph model, which is a very powerful tool for studying graph. So this will be the topic that he will, or one of the model that he will talk about. So I just want to make that an announcement. Because he's also one of my advisor, so I invited him to this seminar. So also this is a seminar that I hold for this quarter. So I already invited 5 speakers. I want to make the announcement that next speaker is a distinguished professor. So, and then he's very good at graph, that kind of analysis. So if you're interested, you can look up from the UCSC schedule to look for the time, the location. The time will be 4 p.m. on Monday. So this is the seminar that I'm hosting. So it's just that the next Monday, it will be him, and then he will talk about graphs. Okay. So look for 280, I think D or D, yeah. Or just look for my name, and then, yeah, and then for stats, 280. The one with my name is the one that I host this quarter. So, yeah, he's a very distinguished professor next Monday. Okay, 4 p.m. Okay, any announcement from you guys, people online or in person? Okay, if not, then let's talk about multivariate normal, and let's do some more analysis, or So multivariate normal distribution. Okay, so we have Y following a normal distribution. I use a subscript n to denote the dimension, and then sigma for the covariance matrix. And just a quick recap. We have Y is equal to a vector y1 to yn. Mu also a vector of mu1 to mu n. Okay, a column vector. Sigma, a n by n symmetric positive semi-definite matrix with the entries of the covariance on the diagonal, and then for the off diagonal, maybe for now let's just put sigma 1 2, and then you can fill in the rest of the component for the sigma ij coordinates. Okay, so that would be the setting. Just to be more precise, n by 1, n by 1, n by n. Okay, that is what we talk about on Tuesday. Let's see what else I need for. Okay, so maybe let me also write down the joint PDF. Later we will also use it. Probability density function for a random vector y, and then the density function 2 pi, a scalar raised to the power of n over 2. N is the dimension of the random vector. Okay, multiplied by the determinant of the covariance matrix, the determinant as a scalar raised to the power of negative 1/2. Okay, multiplied by the exponential part, we have the negative 1 over 2 and then vector y minus vector mu, taking the transpose, so that will be 1 by n, multiplied by the covariance matrix inverse, and then random vector y minus a vector mu. So this will be 1 by n, n by n, n by 1 will return a scalar in the n, or in total, all in everything together will give you a density for a particular, when you input a y. Okay. Any question? Just a quick recap from Tuesday. Okay, so that is the y, and then last time we also talked about or derive a result 1 in the end of the last on Tuesday. Result 1 is saying that if y is following a multivariate normal with mean mu and then sigma covariance matrix, okay. So again, similar configurations. Then let me put it here. AY plus a C. Let's say A is a known matrix with dimension. It doesn't need to be square, so let's put m by n make it more general. M by n, and then y is still n by 1. So that means your C is also n by 1. So this resulting thing, let's call it x, will also have the dimension n by 1. Because y is a random variable, A and C are known or fixed. So x here, which is a linear transformation or a linear combination of a random variable. So x itself is also a random variable. The result 1 is saying when y is following a normal distribution with this mean mu and sigma covariance matrix, x is following a normal distribution with the new mean is a mu plus c, and then the covariance is a multiplied by sigma a transpose. So last time on Tuesday, we derived this distribution with this mean and the covariance through the homogeneous function. Okay, so this is from Tuesday lecture. Any question up to this point? So we use the homogeneous function, and then we derive the multivariate normal distribution, and then we recognize this is the mu, this is the sigma. Okay, so this is for the new variable x. Okay, any question or comments? Okay, and also for people online, if you have question, maybe just speak up. I cannot see if you type in text, so it would be better you just unmute yourself. Okay. Okay, so this is a quick recap from Tuesday, and for today, let's introduce result 2. Okay, similar, we have a random vector y following a normal with mean mu and the sigma covariance matrix. Let me put a subscript in here. Okay, so result 2 is saying AY, also a linear transformation of a normal random variable, is independent of BY, another linear transformation, but with respect to the same normal random variables. They are independent if A multiply, this is a matrix. It can also be different dimension, but here I'm just not going to specify, but it can be, as long as everything is matching, it can be different dimension. So AY and BY are independent if A multiply by the sigma, the covariance matrix from the random variable y, multiplied by B transpose is equal to 0. So here, Okay, so I think, yeah. Okay, so this is going to be 0. Okay, so if you want to be more precise, we can put the matrix A with a dimension, let's say m by n, and then the matrix B, let's say, can be k by n. Okay, so in this one, you will have m by n, n by n, and then n by k. So that means for this 0, it should be a m by k matrix of zeros. But if you can get this matrix become all 0 matrix, then your AY and BY are independent. Okay, so here m and k can be arbitrary numbers. You can also bring them as a, well, yeah, you can just, I'm just using m and k for general cases. Okay, so that means if the result for this is a m by k 0 matrix, then AY and BY are independent. So this is for result 2, and then we are going to show or kind of like to prove this statement here. Any question or comments regarding any of the setting here? Okay. So to show this, we are also going to use moment generate function of a joint probability density function. So the idea is that we are going to first set up the moment generate function for AY, comma BY. And we will also need a vector T1, vector T2. This is the joint moment generate function. What we want to check is that whether this is equal to the moment generate function of AY with a T1 vector multiplied by BY with a T2 vector. If this equation holds, or if this equal sign holds, then they are independent, and then we will see what are the component needed to let this equation holds. And we will see that the component that we need is that this thing equal to 0, this equation holds, and then we know that AY and BY are independent. Okay, so that would be our strategy here. Any question or comments regarding notation, dimension, or our strategy for the proof? Okay. Yeah. So first of all, let's take a look at these two things. Actually, these two components we already have from last lecture, which is just the moment generate function of a linear transformation of a normal random variable. So I will just directly write down. This is also from your Tuesday notes. So the moment generate function, AY, vector T1, this is just the exponential of T1 transpose A mu plus, so this is a plus here, 1 over 2 T1 transpose A sigma, and then matrix A transpose. So the transpose is on this matrix A, and then T1. Okay, so this is what we have from Tuesday. Okay, just additional comments. On Tuesday, we do a AY plus C. So here we don't have the C, we just need a AY part. Okay. And then similarly, BY for T2, we also have the same thing. Transpose B for, and then B mu, and then 1/2 T2 transpose B sigma B transpose T2. Okay. So that is what we have from Tuesday. Back then we have AY plus C, but right now we just need the AY part. So when you plug in to the momentary function, you will have these. Okay, so that means we have the right-hand side. All we need is just to setting up on the left-hand side and see what are the conditions to let the left-hand side equal to the right-hand side. So that would be the strategy or the sketch here. Okay, so now setting the left-hand side. This is the joint, the momentary function for joint. Okay, so AY, BY, T1, T2. So to setting that, use the definition, expected, exponential of T1 transpose. So, well, if you want, you can put a parenthesis for AY. If you want, you can consider AY together as a random variable. Okay, and then plus T2 transpose. If you want, you can also use a parenthesis wrapping BY as BY together is a new random variable. That closing the expectation. So that is the definition of the moment-generating function for a joint PDF, where the joint is referring to this and this random variable. Okay, so that is just applying the definition for the moment-generating function. And then we are going to use the integral to express this expectation. Okay, so here the random variable is still y itself, so y is the only random variable inside this expectation. So now we will just having this function in the front. And then bring in the probability density function for y. This is just the definition for the expectation. So expectation of function is just the function multiplied by the density. This is the thing that we just introduced in the first lecture of this quarter. Yeah. Determinate sigma -1/2 exponential of do I have enough space? Okay, so -1/2. Maybe I'll use the second line. So y minus a mu transpose sigma inverse y minus a mu, closing the exponential. Okay, so dy for the random vector. Okay, dy. Okay, so this dy follow here. Okay, this is just the definition of the expectation. So here to here is the definition of momentary function. This line to this line is the definition for the expectation. Expectation, so what I'm using is expectation of g of x, where x following f of x, this is equal to g of x multiplied by f of x dx. Okay, this is what I'm using. So this thing here is your g of y, if you want, g of y multiplied by f of y. Okay. I will pause a little bit here for you to finish the notes. Any question or comments? Okay. Next, we are going to group just for the following, it's just some algebraic part. We're just grouping things, expanding things, and then to get the terms that we want. Okay, so I'm going to group things in the following way. First of all, the integral. I'm going to bring the normalizing constant for the normal in the front. So 2 pi negative n over 2 determinate sigma negative 1 over 2. Okay, and then I'm going to group this exponential with this exponential. So product of two exponential is the exponential of the sum. Okay, so I'm going to group things together. And for that part, just to ease on the notational part, let's using another letter. I'm just going to define this lowercase b as a multiplied by A transpose multiplied by T1 and then plus B transpose T2. Okay, so what I'm doing here is that I bring the Y outside. So essentially this part will serve as my B transpose Y. Okay, they share a Y, so I bring it outside. So if I call this my B, then this thing inside the parenthesis for this function G here, if you want to call it function G, this is just B transpose Y. Okay, it's just a naming thing. I'm just bring out the common part outside, bring the Y on the right hand side. I call this B, then you have B transpose Y. Okay, just for notational simplicity. Okay, then I'm going to combine this by and then this one here. So I will have the exponential. Let's see. What do I want to call it? Can I call it? So if I call this my B, then B transpose is my T1. Okay, so now I'm just going to call this B transpose Y minus 1/2 Y multiplied by mu transpose sigma inverse Y minus a mu, closing that, dy. Okay, so I'm calling this thing as my B transpose Y. Exponential is just the sum of this term plus this term. So I have by, B transpose Y minus this part. That's just grouping them together. Any question or comments? So I'm just using the lowercase b so that I don't need to write the whole things here. Okay. Yes.
Is there a reason you're doing the transpose of it instead of just keeping B as is?
What do you mean by?
Yeah, I'm just saying.
You mean the transpose for B?
Yeah. Is there a reason you're keeping it as B transpose Y as opposed to like Y B or something? Like, is it going to be used later on maybe?
Yes, the reason will be I'm going to use later or to make it easier for some cancellation. Yeah, but right now, yeah, I might. That's a good question. You were just saying why using B transpose Y, not Y transpose B. Is that your question, or
Y B, right? Because if you flip them, you should use the transpose, right? But or not necessarily. You didn't confuse us.
Okay, so if I define this as my B, okay, so let me double check. So B transpose Y is A transpose T1 plus B transpose T2 transpose Y. This will give me T1 transpose A transpose is just A multiplied by Y plus T2 transpose B transpose and then Y. It's just this one. So here I didn't change anything. I just copy this way, and then B transpose Y is just equal to that. I did not change any order or things yet, yeah. So if I call B equal to that, B transpose Y is just this thing here. Right. Yeah, so I'm just rewriting this as B transpose Y. I did not do anything else. Yeah. But the purpose, if that's your question, the purpose is just I don't need to write the two sum. I'm just writing B Y. That's it. B transpose Y for simplicity. Okay. So what we are doing here is that we express the left-hand side of the things that we want to prove as this expression. Okay, so now let's leave this expression as this way for now. Let's examine a following things. Okay, so here let's deviate, or let's take a detour. So just let this expression be like this for now, and let's examine another term. Okay, so let's call examine the following terms: y minus sigma multiplied by b plus mu, closing the square bracket, transpose sigma inverse y multiplied by sigma multiplied by b plus mu. Okay, so now we are leaving the terms that we just have. So we're not going to work on this for now. Let's take a look at another terms, and then my goal here is that I'm going to work on doing some expansion on this term. Later you will see the connection of this term here with the expression here. Okay, so now what we're doing is that we step away from the equation that we're interested in. Let's examine another new terms. This thing is the new term that I construct, and then what we're going to do is that we are going to expand this term, and later you will see the connection between this term that I construct here, or that I propose here, with the quantity of interest. Okay, so that will be our strategy for now. Okay, so now let's take a detour and let's examine this part. Okay, so let's see. Okay, so let's examine this new term. Okay, so this term equal, so we're just working on this, and then I'm going to do it for y minus a mu. So y minus this mu and minus sigma multiplied by b. Okay, I'm just grouping the parenthesis. I did not change anything so far. Sigma inverse y minus a mu minus sigma b. Okay, I'm just breaking the parenthesis, grouping y minus mu, and then minus the third term. Okay, now I'm going to break the square bracket. So one way you can think about this is that you can have a minus a b, I mean in scalar, c multiplied by a minus b. I'm going to do ACA, ACB, and negative BCA, and then BCB. And then I'm just going to break the square bracket. That is what I'm going to do now. Okay. Let me pause here and ask if any question or comments, or if any details that needs to be elaborated. Okay, so we're going to examine this term. I first changed or grouping different things in a different parenthesis. Now I'm going to group or break the square bracket. Okay, so here I'm going to have y minus a mu transpose. So this multiplied by sigma multiplied by that. Okay, so this is A minus a B, C, A minus a B. So this B is not the same B. I'm just using kind of like a scalar case for you to understand what I'm doing. So this is ACA. Okay, now I'm going to do ACB. Let's see. Or maybe let me do BCB. So let me just group this and this and this. Okay. So this is plus B transpose sigma transpose is sigma itself, sigma inverse sigma multiplied by B. Okay, so in the scalar version, this is A, C, A, this is B, C, B, and also that means we have two copies of A, C, B. Does that make sense? I'm just going to distributing the three terms. So ACA, ACB, and then BCB. Okay? Any question or comments? Yes.
Anytime you get a problem like this, is expanding the term going to be the first thing that we want to do?
Expanding which part?
Or what you're doing now, is that not expanding?
Yes, we are expanding, yeah.
Like for all questions where it's easy, I mean, is this the common, like the standard way for us to do?
Yes, actually, another way is that you can do it the opposite. You can expanding this and see if you can get this one here. So right now, I'm kind of like doing I know the answer, so I do it in this way. So my reason is that after I expanding this, you will see that it ends up with this. So actually, these two things are the same. One way to do is that you do manipulation construction to this term, you will end up with this. Another, what I'm doing here is that I decompose this, and then you will see it ends up with this. So this is all by design, and then actually, so this is kind of like so like lots of things we do plus 1 and minus 1. So we are designed the plus 1 and minus 1 and then utilize them as a mathematical tricks. Yeah. So I'm
trying to figure out how we should go about this if we don't already know the answer.
Yes, that's a very good question. I think you just do a reverse engineer from here to here. Yeah. Right now what I'm doing is that I know the answer, so I'm showing you the opposite way. Yes. So this thing here is equal to this, but it's difficult to do it in this way. But I'm showing when you're expanding this, you will get this. So they are the same thing. Yeah. But I just want to show in a kind of like a reverse engineering part. Yeah. Great question. That's a very good question. Any other question or comments? Okay, so now let's consider the minus 2 ACB. Okay, so I will need a minus 2 times y minus a mu sigma inverse, and then D sigma multiplied by B. Okay, so this is A, C, B, and then you have 2 times. So there's a 2 here in the front. And also this is a minus sign because this is A minus B multiplied by C. Okay, so this is a plus, this is a plus, this is minus 2.
What's happening to the transpose of the y minus mu in the last term? Are we?
You mean here?
Yes.
Perfect. Yes, typo. Thank you. Yeah. This the one you say?
Yeah.
Yes. Thanks. Yeah. So n by 1 transpose will be 1 by n. This is n by n. This is n by n. This should also be I mean, I did not specify, did I specify A or
Yeah.
B? Okay. So that would be, can you repeat what I wrote down, the note? Can I mention the dimension? What is A?
A is m by n, so A transpose is n by m.
M by N. Sorry, what's A transpose?
A transpose is n by m.
N by M. Okay, T is M by 1 then. And what is B transpose?
B transpose is n by k.
N by K, and this is K by 1. So I will have N by 1 and then N by 1. So B is N by 1. Right? I did not make any typo. Right? Okay, perfect. So B is N by 1. So yes, this is N by N, this is N by 1. So the whole thing should be a scalar, right? Thanks. Yeah. Okay, what else? Yes,
For
go
the
ahead.
minus 2 ACB,
Yeah.
you can only, it's only the ACB and BCA are only,
Symmetric.
you can only, yeah, you have to be symmetrical for you to combine them as like terms, right?
That's a good question. Let me see if that's symmetric.
It is symmetric, so that, like, this part makes sense.
Yes, yeah.
Generally, you have to check that it's symmetric.
Yes, yeah, that's a good point. Yeah, but they're symmetric.
Yeah.
Yeah. So the question or the concern raised here is that y minus a mu transpose sigma inverse sigma b how should I write it? This transpose is equal to this, right? Yeah. So you need to verify they are the same. Then you can group by 2, right? Yeah. If they are not, then you have to write minus ACB and then minus BCA, right? If they are not matching. Yeah. That's the concern raising. But in this case, they are symmetric, so you can minus 2 copies of that. Yeah. Good point. Yeah. Thank you. Yeah. In this case, they're symmetric. You can use the 2. Yeah. Yeah. These are all good points. Any other comments, thoughts? Okay. Now let's continue our expansion. So, okay. Before we do that, let's group some of the things together. So this part can only stay the same. This part here, mu, so multiply an inverse by itself, it just ends up with identity. So you will have B transpose sigma, 1 copy of them, because this will be identity dimension n, so you will just have this minus also a minus 2 copy y minus a mu transpose. These two cancel out, so I'm just going to write a b here. Is that correct? Yes, yeah. Okay, and now I'm going to further decompose this thing here. Okay, so that's what I'm going to do next. So y minus a mu sigma inverse y minus a mu so I'm going to do 2y transpose b and 2 mu transpose b. Okay, so you minus 2y transpose b and then plus 2 mu transpose b. Okay, so let me pause here and do a quick summary of what we have been doing so far. So first of all, we are interested on this joint moment-generating function. So we expanding the term, and then we get an expression that look like this. That's the joint moment-generating function, the quantity of interest that we are interested on the left-hand side. And then we take a detour, we examine the thing here that I proposed. Okay, so here just something I proposed, and then we expand the terms. We observe that it equal to something that look like this. Okay, so now let's make a connection between this and the actual quantity of interest. You can see that the actual quantity of interest is b transpose y minus a this. Okay, and let's see if we have that in our construction. We have this one is included in the construction or in the quantity of interest. The other one that is also included is the b transpose y. This is also included. Okay, so from the expression that we constructed, there are two additional terms that are not in. Let me not use x, but they are not included. This is also not included. Okay, so from our so that means the terms that we examine actually having additional these two things that are not included in the quantity of interest. Okay, but it also involving something that is included in the original quantity of interest. So now let's plug in this back into the quantity of interest. Okay, so now just to make the connection. Any question or comments, or if anything is unclear based on the strategy here? So now I'm going to make the connection with the terms that I propose back to the quantity of interest. Okay, so here, let me write it. Original term of interest. Let me call this star, and this star I'm referring is this one here. This is the star. The things that we are actually interested, but we take a detour by examining this term. We saw that the term that I proposed here actually involving all the terms that are included, but just having 2 more additional terms. So that means the star here. So continue from this line here, the quantity of interest. So I'm saying that the star is equal the integral of 2 pi negative n over 2 determinate 1 over 2 exponential. And now I'm going to rewrite the star in terms of the quantity that I propose here. Okay, I'm going to use this one inside the original quantity of interest. So we still have 1/2. Maybe let me use a curly bracket. Okay, so the terms that I introduced, sigma b plus mu transpose sigma inverse y minus sigma b minus plus a mu. Okay, so if I stop here, closing the curly bracket and then dy, does the equal sign holds or not? It does not hold, right? Because this term here ends up with 2 additional terms that are not in the original terms, right? So what should we do here? Minus them, right? Removing them from the picture, right? Okay. So, do I have a sign difference?
You have to take the transpose and factor out a negative 1/2.
Yes. So if I factor okay. Yes, yeah, you're correct. So now I'm okay, so that means okay, so this expression here is saying that I added a negative 1/2 in the front, right? So I need to bring the negative 1/2 to each of the terms, and then I'm removing them from this picture, okay? So if I added a negative 1/2 to this one, so that means I will have a negative 1/2 B transpose sigma B. But I want to remove them, so I need to change the sign again, right? So I need to add it back, right? So this means I should adding a 1/2 B transpose sigma B. Okay, does that make sense? So this is saying that I'm adding a negative 1/2 to the whole things here, okay? So I will have a negative 1/2 B transpose sigma B. And then I want to remove it from this picture, from this term here, So I need to take another minus sign. That makes it a plus, adding 1/2 B transpose sigma B. So that's why I have a plus and then also a negative 1/2. This is just to remove from this quantity, because this quantity involving a negative 1/2 B transpose sigma B. I want to compensate the same term. To make the equal sign still hold, I need to add it back, okay? And then the adding, this plus sign here is because we have a negative sign in here. Does that make sense? Right. Okay. And similarly, we should also have negative 1/2 of that, but we need to flip the sign, and that will make it also plus, right? So plus 1/2 multiplied by 2 mu transpose B. Now I'm able to close the curly bracket and then dy. Okay, so a quick summary here is that the star, the equation from the original quantity of interest, can be rewrite as this part. And this thing here is the one that we do it construction or that we do it by examination. Question? Oh, give me 1 second. From the examination. And then we remove these from the picture. And then we can, using the construction terms, to replace that. Yeah, question?
Do you have to take another transpose? Because you substitute B transpose Y with a Y transpose B.
Which part? Which term?
So your original term of interest has a B transpose Y, but you substitute that with a Y transpose B. And when you expand the terms, it's almost fully simplified. Right there, it's Y transpose B.
Okay, so first of all, let me double check what is the dimension of B. The reason, if you want to be very precise, is yes. But the thing is that this is 1 by n, this is n by 1. It's a scalar, so scalar transpose is just itself.
Right.
Yeah, right. So in that case, it doesn't matter. Yeah. But if you want to be really, really precise, then B transpose Y, right? That's what you were saying, right?
But
But
I'm talking about for like the next term, you'd have to take you'd have to do like. B
what do you mean by
transpose
next term?
For B transpose, or for mu transpose B?
This is also scalar, right?
Yeah.
Yeah. So yeah, if you want to be precise, then you have to, you were saying this is Y transpose B, right?
Yeah.
And here I have B transpose Y, right? But this is scalar.
Yeah.
Yeah. So yeah, if you want to be precise, you need to take a transpose, but it's a scalar itself, right? So the question is that this thing, our original quantity of interest is B transpose Y. Through our construction, we end up with Y transpose B. So that means we need to take a transpose. But the thing is that all these things are scalar, so if you take a transpose or not take a transpose, it just itself. So it doesn't matter, or yeah, in this case. Yeah. Okay, so next let's continue from the star, or let's continue our equal sign. Now I'm going to bring, so here, the things I'm underlying here, they are constant, right? They does not involving the random variable y that we are interested in, or we are working on. So I'm going to consider them as a constant term. I'm moving outside the integral. Okay, so I will have E of mu transpose B plus 1/2 B transpose sigma multiplied by B. Okay, So these are the constant, they are in the exponential, so I'm going to move it outside. Okay, so this is a constant. And then let's put the remaining thing inside the integral. Let me still use curly bracket, -1/2, square bracket, y minus, parenthesis, plus mu, closing square bracket, transpose, sigma inverse. Okay, so maybe let me start from a second line, also a square bracket, the same thing, plus mu, closing square bracket, closing curly bracket, closing the integral by dy. Okay. Okay, does it look good? So, yeah. Now, let me ask you a question. What is the thing inside the integral? What does it represent? That's the thing that we started with the construction, the terms that we examined. This is the term, the extra term, but they are all constant, so we can move it outside. So this is the thing that is coming from the construction. Okay, the part that we examined. So then let me put it, this is constant. Okay. So what is the thing inside the integral here? What does it represent?
Multivariate normal distribution of sigma b plus y, comma.
Okay, so okay. So this is a normal distribution, right? What is the mean there? Is that what you're saying, right?
Yeah.
There's a normal distribution, right? What is the mean?
Sigma b plus mu.
So your mean is your sigma b plus mu. They're all just parameters, right? Constant. What is your variance here?
Sigma.
Still the sigma matrix, right? Okay, so now we're recognizing whatever inside the integral is a density function, right? It's a normal density with this mean and this covariance matrix. And now, okay, so this is the density function for this y. So if we do the integral here, what does it equal to?
1.
Just equal to 1, right? So again, the star is just equal to E for the constant part. Mu transpose B plus 1/2 B transpose sigma B. Okay, so let me just, in case you forget, this is the moment Jenny function of AY, BY, T1, T2, our quantity of interest, okay, the left hand side, right? Okay, to finish our, or to prove the claim here, we now have an expression for the left hand side. We now have an expression for the right hand side. Now we just need to see that under which condition the left hand side equal to the right hand side. That is what we're going to do next. Okay, so the star is for the left hand side. The things here, these are called the right hand side. Okay, so let me call right hand side. And then the star, let me put it here. This is the left hand side, or the star, if you want. Okay, so now we are just going to match these two things. Okay, so okay, let's continue on the left hand side. And also one thing I want to mention is that don't forget the B here. So don't forget that B is equal to A transpose T1 B transpose T2, okay? So this is saying that the star equal to mu transpose. Then let me use square bracket for this. Can someone read the B for me? What was B? From the
Exponent of T2 transpose.
no A, the B here. What is the B? The A transpose
A transpose
T1
plus B transpose T2.
T2. This is the one that defines the lowercase b, right? Okay, and plus 1/2 B transpose again. So let me bring in the B. So B is A transpose T1 plus B transpose T2. This thing transpose sigma B itself. Okay, again, A transpose T1 plus B transpose T2. Okay, so what I'm doing in this, from this line to this line, just plug in my expression for B, the one that I define, lowercase b. Okay, so just plug in B. Okay, one more step. Just keep expanding the terms here. Let me write it in a way. Okay, so maybe let me now just write it mu transpose A transpose T1 plus mu transpose B transpose T2 plus, okay, so here's the same thing, A plus B multiplied by C multiplied by A plus B. So I'm going to do ACB, BCB, and then 2 copies of ACB, right? So I'm just doing the same thing. Okay, so I'm not going to do it explicitly. I'm just going to write down all the final 3 terms here. Okay, 1/2. So don't forget there's a transpose here. So T1 A sigma, right? There's the transpose is on the A on the right hand side, T1, to ensure this is still a scalar, right? So this is ACA plus BCB B transpose T2. Okay, so this is ACA, BCB. We have 2 copies of ACB, and the 2 will cancel out with this 1/2. That means plus the 2 will cancel out with this T1 transpose A sigma B. For the B, there's a transpose T2. Okay, and we are able to close the square bracket. Do you agree with that? I think now we complete the left hand side. So now you can see that. So this is the, again, just to remind you, this is the star, or the right hand side, or the quantity of interest, what the thing that you want to call it. The left hand side, yeah, this is the left hand side. So the left hand side is equal to that. The right hand side is the product of these things. So you can see that you have this term, you have this term, Okay, so maybe let me give them a number. So circle 1, circle 2, circle 3, circle 4. Okay, so this is the right hand side. You have these 4 things. Let's go back to the left hand side. This is your circle 1. This is your circle 2. This is your circle 3. This is your circle 4. So you can see that the product of the right hand side right now is still not equal to the left hand side unless this thing here equal to 0. Okay, then left hand side equal right hand side when A sigma B transpose equal to a matrix of 0. Okay, so this condition here, when this equal to 0, shows that the joint homogeneous function is equal to the product of the marginal homogeneous function. In other words, AY independent BY when this equation equal to 0, or the left hand side equal to the right hand side when this condition holds. Okay, so what we have shown here is that AY, two linear transformation of a normal random variable, they are independent when the transformation, the A multiplied by the sigma multiplied by B transpose equal to a matrix of 0. So that is what we're showing, the result 2. Question or comments?
Could you scroll up to show like the way you number the terms?
Sorry, can I say that again?
Yeah.
Oh, this one? Yeah. I think I used the first one, the one without involving A is 1 and 2. The thing involving B is 3 and 4. Yeah. This is the 5th term, but when this equal to 0, it disappears, then they are equal. Later, we will apply all this result in many of the hypothesis testing and also linear regression. So when you fit a model, all these results will be useful to show their independency there. Okay, so I think we have 25 minutes. I have another big result to show, but I'm not sure if I can finish in 25 minutes. Okay, if that's the case, then let's do some more, any question up so far? So what we are doing is just doing the proof or trying to show the result 2. The result 2 is saying that linear transformation of normal is independent of another linear transformation of normal when this equation holds. Okay, so since we only have 25 minutes, I'm not able to show the next big result, so I'm going to just some additional comments on some of the details. Okay, so the next thing, any question before we start? Okay, so now I'm going to talk about spectral decomposition of a symmetric matrix, or in our context, we are just interested in the sigma matrix. Okay, spectral decomposition. I think people sometimes also call singular value decomposition. Yeah, but I'll just call it spectral. I like to call it that way. So spectral decomposition, and I'm focusing on this part, this matrix. But as long as they are symmetric, you can perform this decomposition, right? So Okay, so this matrix satisfy the symmetric part. So you are able to do it for the spectral decomposition. So I'm focusing on spectral decomposition of this covariance matrix. Okay, so the spectral decomposition for that, n by n, is equal to p. So this notation here, I'm referring to the capital lambda. So lowercase lambda is this one, capital lambda is this one. Okay, so that will be my notation for the capital lambda. P transpose. Okay, so here the P is so first of all, this is a n by n. This consists of the normalized eigenvector in the first column, the second one column until the nth column. So I'm going to represent them in the column. I'm going to attach them in the column wise. The lambda matrix, also n by n, but this is a diagonal matrix with the corresponding eigenvalues on the diagonal. The rest are zeros. Okay? And then you can do this to construct your original covariance matrix, but you can, this is valid for symmetric matrix, but right now we're focusing on the covariance matrix. So this is called normalized eigenvector. They are normalized in the sense that EI transpose EI, so when they're indexed, so the column inner product with the same column, which is a scalar, and this scalar is equal to 1, then it's called the normalized version. EI transpose EJ equal to 0 for I not equal to J. So after you normalize it, you will have that equal to 0 and equal to 1. Okay, with this here, you can also deduce that P transpose P, what does that equal to? So you're using the column multiplied by its own row to get your first elements. And then for each of the ij pairs, you will get 0. So that is saying you are going to get an identity matrix dimension n, right? P transpose P. You will notice that if this equation holds, this is saying P transpose serve essentially as the P inverse. Then you will have the same thing that PP transpose also holds or also equal to identity matrix. So you can see this by, if you consider this as your inverse, then if you right multiply it, you will also get the identity. Okay, so here are all the things that the equal sign holds. Okay, I think also on Tuesday, someone mentioning about what is the purpose for the negative inverse for the covariance matrix. So I think, let me put it on here. Then here are some additional results. Covariance matrix inverse equal to the spectral decomposition, but you take the inverse for the diagonal elements there. Okay, so the capital lambda is the eigenvalues. Here the eigenvalue need to match the eigenvector, okay? So to get the inverse of that, all you need to do for the spectral decomposition, you can just take the inverse of that. So when you take the inverse of a diagonal matrix, so you just have lambda 1 1 over lambda 2, 1 over lambda n for your lambda, capital lambda inverse. Okay, that is what I'm referring to. You just take the inverse of the diagonal elements because the off-diagonal elements are all zeros. Okay, then the second one, if you're raising to the power of negative 1/2, this is the same as you raising to the power for the eigenvalues for the negative 1/2. And then similarly, raised to the positive 1/2, it just raised to the positive 1/2. Okay, so based on these, you can also have a fourth equation, sigma 1/2 multiplied by sigma 1/2. Let me put it, okay, I think I have here. Let's bring in this one, P sigma, a lambda 1/2, P transpose, P lambda 1/2, P transpose. What does these two equal to? Okay, so you have P lambda 1/2, lambda 1/2, P transpose. What does these two equal to? Lambda. You have P multiplied by lambda, P transpose. What does this equal to? Sigma matrix. So you have the connection 1/2 sigma matrix raised to the power of 1/2 multiplied by sigma raised to the power of 1/2. You have the sigma matrix. So here again, the capital lambda are all diagonal matrix. Only main diagonal has value of eigenvalues. All the off diagonals are zeros. So that's why when you take the product, this is equal to you raising the power of 2 for the diagonal elements, ends up with this one. Okay. This is identity by n that we just show on top by the normalized version of the eigenvector. Similarly, let me write it here. 5 sigma 1/2 multiplied by sigma negative 1/2. You will have this negative 1/2 P transpose. Okay, so the P transpose P is identity. This one multiplied by that is that you're taking the square and also inverse. It will end up with P capital lambda raised to the power of 1/2. So this is kind of like you square them. You have negative 1/2, negative 1/2, you have a negative 1. P transpose, this is equal to sigma inverse. Sometimes people call this the precision matrix, and the not inverse version, the covariance matrix. So sometimes the inverse will also be useful in your statistical analysis. Okay, I think we have 15 minutes. Okay. I will close today's lectures by introducing one more. Any question regarding these? Okay, I will end today's discussion by introducing a topics. Also, I want to mention that if you are interested in this research topics, I have a favor to ask if you are not too busy. If you're really interested in this, then I have a research project for you for the distribution of quadratic forms of normal random variables. If you're interested in these topics, you can email me. I have a research topic on this. I have a research project on this. distribution of quadratic form of normal, let me put RV, random variables, okay? So besides graph, I also have other this projects if you are interested, okay? So I'm going to talk about the distribution, quadratic form, normal variables. Okay, the first result, okay, or if you want result 1, so here, let's say for scalar, z1, z2, zn, they are scalar for now, IID, independent, identical, distributed, standard, normal, 0 and 1, okay, again, scalar. Then you can concatenate them into a vector n by 1, so make them a column vector n by 1. Then you can write it normal subscript dimension 0 mean vector identity covariance matrix. Okay, so when you concatenate them into a vector, your multivariate normal mean of 0 vector covariance matrix identity dimension n. We know from the previous result, when you square the scalar version, sum them together, also this is equal to vector inner product vector, so this thing following chi-square degree of freedom n. Okay, that is how you can construct a chi-square from sum of square of normal. Okay, so when you do z transpose z, it's essentially you squaring each of them, sum n copies of them, you will get a chi-square random variable. Okay. Two. Okay, so now let's start from also a normal vector, but we are no longer identity covariance matrix 0, and then let's add a sigma term multiplied by identity. Okay, so now they are not standard normal. So this is saying each of the elements, they are still independent, identically distributed, but they are distributed by 0 and the covariance sigma, where sigma does not necessarily need to be 1. It just needs to be sigma squared. Okay, this is what this this matrix, the result 2 is different from result 1. Okay, then to construct a chi-square, so here I'm using the scalar version, minus the mean over the standard deviation. Okay, so this is how you normalize a general normal distribution, minus a mu over standard deviation. Taking a square, you're just squaring a standard normal, sum n copies of them, you are still going to get a chi-square degree of freedom n. Okay, so we are just following the same thing but doing one extra transformation. And if it is not clear, this is saying sigma square, all the way sigma square this matrix. Okay, 2 is just one more step, one more transformation comparing to 1. Okay, let's do 3. Let's consider a more general normal. Let's use y following multivariate normal with mean mu and then sigma square identity. Okay, and also sometimes people, or in machine learning community, people call this isotropic normal because you only have the diagonal covariance. You don't have the covariance term, they are all zeros. So people call them isotropic normal. Okay, so this version is still an isotropic normal. And if you starting with this normal distribution, give me 1 second to adding one more comment. Sorry, for result 2, I want to add one more comment here. Because right now, I think by now you should be very familiar with matrix vector multiplication. So this is saying Z transpose Z over scalar sigma squared. Okay. I just want to add this one here. So in scalar version, people usually use scalar square summation. But for vector matrix multiplication, Z transpose Z divided by scalar, this is the same operation, okay? Chi-square n, okay? Then for a more general normal, now we have a mu instead of 0. You can do summation. You can do summation from 1 to n yi, the ith elements in this vector, minus a mu divided by sigma. This is variance, this is standard deviation. Standardize it, taking the square. This is saying you have y minus a mu transpose y minus a mu. These are vector inner product divided by a scalar, and here you need to take the square because this is a quadratic form here, and this square here is taking from here. So you need the square in the denominator, and then this will go back to chi-square degree of freedom n, okay? So if you start from a normal with this one, if you do this standardization, you still have a chi-square degree of freedom n. Okay, let's start with a more general normal. This normal does not need to be an isotropic normal. So for y, following multivariate normal with mean and a general covariance matrix sigma. So you can see that for this one, for 4, comparing to 2 and 3, is that you have elements on the off diagonal, right? So it's no longer isotropic normal. Okay, if you started with this, you want to get a normal distribution or a chi-square distribution, you will need to do, let's call it V. You need to do the sigma matrix raised to the power of negative 1/2 multiplied by y centered by mu. Okay, so this thing here, so up to this point is still a standard normal. And then if you do V transpose V, you will get a chi-square degree of freedom n. Okay, so this is more, if you started from a more general case, if you do V transpose V, you will get a chi-square. Okay, one thing I want to do here is let's examine this V matrix, this construction here. So first of all, this is a linear transformation of a normal random variable, right? This is AY plus C, right? So V following normal, that checks out, right? The question is, why is this 0? Why is this identity? So let's verify that. Expectation of V equal to expectation sigma 1/2 y minus a mu. Then maybe let me use square bracket to distinguish this. So expectation is a linear operation. Then I can bring in the expectation inside. What is the expectation of y? Where y following this?
Mu.
Just mu, right? This equal to, so we have mu minus a mu, we have a 0. Okay, So we check out that the mean for this normal is a 0. Okay, I'm going to move this equal sign to the top. Okay. So V is a linear transformation of normal. We know it's normal. That's from result 1, the things that we show on Tuesday. Taking the expectation, you have mu minus mu, this is a 0, so we check this one equal to 0. Now, let's take a look at the variance of V. This is the variance of negative 1/2 y minus a mu. If you want, you can also use square bracket to distinguish the parentheses. Okay, for this one, I'm not sure if I show the formula for. Have I shown like formula for variance like a y? The variance of a y is equal to a variance of y multiplied by a transpose. Have I showed that formula?
It came up in section.
Essentially, okay. Great. So the variance of this. Okay. Let me do one more elaboration then. So this is variance sigma one half multiplied by y minus sigma raised to the power of 1/2 multiplied by mu. So this thing is a constant. Do you agree with that? With respect to random variable, this is a constant, right? Shifting a constant to a random variable does not change a variance. Do you agree with that? So I can set the line equal variance by scaling factor for a random variable y. So the constant here, shifting, does not change the variance, right? I can write it in this. Now I'm going to apply the formula sigma 1/2 sigma. Okay, let me take one more step back before I jump. Okay. Variance of y sigma negative 1/2. Okay, the formula I'm using here, that you were saying is in the section, is so in the discussion. I guess you already talked about this. So this is the formula I'm using. So note that the A transpose is on the right hand side, right? From the lecture, from the discussion. Okay. So you can check your notes on the discussion. So the A transpose is on the right hand side, okay? So this is a matrix. And this one, when the transpose is symmetric, so it stays itself. So this is the formula I'm using from this line to this line. Okay, negative 1/2 sigma negative 1/2. And I'm going to write, okay, so if I write here positive 1/2 multiplied by negative 1/2, do you agree with that? So one way you can show this multiplied by that is positive 1/2 through spectral decomposition through this one here. You have negative 1/2, positive 1/2, you will get, yeah. So you can use this to get the result from here. You can use spec decomp to get this 1/2, and again 1/2 negative 1/2 identity degree dimension n. Okay, so we verify that the variance of V is also identity. So we check out everything. This is standard normal. Then we apply the same transformation, V transpose V, become a chi-square degree freedom n. Okay, so I think I'll stop here, and then I will have one more big result based on all these details that I introduced today to introduce the next big result. Okay, thanks. I will close the meeting on the Zoom as well. Okay, I'm going to close the, let me pause.